start a new lecture today. So Professor Michael Schmitt from Northwestern is going to be telling us about statistical methods aimed at theorists. So he promised to be very nice to us. Michael is a particle physics experimentalist who's been involved in lots of different things, from LEP experiments to the CDF experiment at Fermilab, and he's now a member of CMS, and he's also a member of the mu2e experiment. So that means you can ask him anything about anything that has to do with particle physics experiments. And he's also somebody who spent a lot of time thinking about statistics. So he will try to give us some flavor of that. So whenever you're ready.
Thanks a lot, Andre. Appreciate the kind words. I have to admit the only part of particle physics I have no contact with, really, direct contact, is neutrino physics. So you have to be kind to me about that as well, since I'm not a neutrino physics expert. But statistics is statistics, and I hope to give you in a mere 3 lectures at least a good grounding of all the key concepts in statistics. We obviously won't be able to do extremely advanced, complicated technical things, but after all, this is not a summer school on statistics, this is summer school on physics, so maybe this works out well as a little kind of addition off to the side of the main things. So as you know from looking at the schedule, I've been asked to give 3 lectures today, tomorrow afternoon, and then Thursday morning, because there was a little bit of a change of the schedule. In this first lecture, I'd really like to go through very fundamental concepts. Maybe some or many of these things will be familiar to some of you. I hope not to be too tedious or too boring in that case. Tomorrow we'll talk about things like parameter estimation, fitting, curve fitting, this kind of thing. And then the last day will be mainly about hypothesis testing, which sounds sort of obscure and you know, peripheral to physics, but it's actually really at the middle, especially in neutrino physics, where there are questions you want to answer. So I hope that the third lecture turns out to be the most interesting one. Okay, now in terms of my technique, I have lectures here that I've written on a PDF file. In fact, if you want to look, I've already uploaded today's lecture to the wiki page, so you can download that and scribble on it as you like or follow along as you like. I also have a pen, and so I will try to write as necessary to answer a question or to underline a point. Okay, but in principle, we don't need me to write to see these slides. All right, so let's dive into it. I want to start at the very, very beginning. You're theorists, so you like to think about abstract things. So we're going to start with something a little bit abstract by concrete examples, a little bit backwards maybe. All right, so I want to tell you briefly about events and sample space, just telling you what it is. In the usual language of statistics, we talk about an experiment, but an experiment is not like Dune or Sevens or CMS or something like that. In this case, it's something that you do or something that you observe that has a real outcome, something that you can specify. For example, you can toss a coin as an experiment and say that you observe a heads or a tail afterwards. Or maybe you're working on a liquid argon neutrino experiment and you're considering that a photon hits a photon detector of some sort, okay, et cetera, et cetera. So the point about what is an event and what is a sample space is that you have to have well-defined, well-identified outcomes, and also the experiment or the event is something that you firmly have in mind, okay? Here's a kind of simple picture of a sample space. It's an abstract picture. You could have a sample point inside this sample space that would be a unique outcome, like a coin coming up heads. Or you can have an event, meaning a group of sample points, which is simply basically a subset, an arbitrary subset of the sample space. And again, I want to emphasize that the event that we talk about here is not the same as an event in particle physics, such as a neutrino entering a detector and producing a muon tracker or something like that. Okay. Now, if we were rolling, for example, a single die, there's a picture of a die, there are 6 sides to it. So we could specify as an example, event A, getting the number 3 on top, event B, getting a number on top that's an even number, or event C, getting an event that is a number greater than 4. An elemental event is one that is single, cannot be reduced to anything simpler than that. So obviously event A is an example of an elemental event. A compound event is one that consists of 2 or more elemental events, and so events B and C are examples of that. Now, elemental events are mutually exclusive by definition, while compound events will in general overlap. So given these 3 examples, it's obvious that getting an even number and getting a 3 are mutually exclusive. So the intersection of them is the empty set. However, the union of B and C is not empty. The point, this is all elementary stuff, simple set theory, but ultimately you should think about the sample space, right? This part here. The sample space should really be considered as the union of distinct non-overlapping elemental events. Okay. Now, with this picture in mind of throwing a die, for example, I want to say a little bit about classical and frequentist probability theory. So the classical approach, due to Lagrange, for example, Laplace, is that you sort of identify all the possible elemental outcomes in such a way that each outcome has the same probability of occurring. So if you flip a coin, there are 2 possible outcomes and they both have 50% probability of occurring. So if there are n such outcomes and each event corresponds to m of them, then the event is simply the quotient m over n. So again, the probability of getting a heads when you toss a coin is 1/2 because m is 1 and n is 2. It's as simple as that. And this, of course, is great for calculating probabilities of getting cards if you're a poker player or something like that. The other approach is a frequentist approach. And in this case, the idea is, well, let's just find out empirically what is the chance of observing a head or of getting the number 3. We'll take the die and we'll throw it 100 times. We'll count the number of times that we see a 3. And then the probability for the frequentist is just that fraction of the number of times that you observed a 3 when you toss the die. And formally speaking, that probability you would take in the limit that you toss the die an infinite number of times, okay, or at least many times, right? So these are obviously 2 rather different ideas of how to calculate a probability. And they're both actually have serious difficulties. Maybe you notice this right from the start. In the case of classical probability theory, we said we're going to define things that have the same probability, you know, like the 6 sides of a die. But that's circular, isn't it? How can you define probability in terms of things that have the same probability? So it's maybe obvious for cards what this means, but how would you do this in terms of the more sophisticated analysis like the probability for coronavirus to spread in a city or a town or something like that? Frequentist case, it's not possible to take n to infinity, and the actual answer will actually vary each time you try to determine it. So the answer is not unique. Usually, that's a no-no in science and mathematics, right? If you calculate something, you should get a unique answer every single time. It should be the same answer. It should not be random or stochastic. So both of these conceptualizations have some serious difficulties, but nonetheless, they help us to grasp some things about what's going on. I'm going to skip this. So things kind of stumbled along with those 2 inadequate discussions until 1933, when Kolmogorov said, I would like to put probability on axiomatic basis, say like geometry, in order to bring probability theory into the realm of serious mathematics. And these are really remarkable. He said, given a sample space E and some elemental events E sub I, perhaps 2 compound events A and B, and then a probability, which is a real function mapping events onto the real numbers, then there are these axioms. And there are only 3 of them. The first says that that probability for any elemental event is not negative. The second one is that the probability of 2 different disjoint elemental events is simply the sum of the probabilities. And finally, the probability of all possible elemental events, or the sample space as a whole, is unity, which just means, you know, that something has to happen. That's what it means to say P of S is 1. And immediately you can prove, you can do this as an exercise if you like, you know, several other useful, sort of complicated looking consequences, axioms, or let's say theorems as follow from these axioms. And indeed, this is sufficient as a consistent mathematical system. So that's great.
Michael,
yes?
there's a question in the chat.
Oh, great, thank you. Pranjal says that it seems that the classical probability is based on assumption. Pranjal, yes, you got exactly the point. I'm very happy you make that comment. It's exactly right. If we go back to this business of the die, you would say the probability of getting a 3 on top is 1/6 because there are 6 sides. They're all equally likely. And therefore the probability of getting a 3 is 1/6. But the point is, and it's exactly what you said, that we're assuming the probability of all sides is the same. And for the die, maybe it's constructed to make them the same, but they're the same to what degree? So the weakness of the classical theory is that it necessarily involves assumptions that may or may not be true. The weakness or advantage of the frequentist approach is that it makes no assumptions, all right? And it just says that we're going to determine the probabilities empirically, and to the extent that we do a good job, we'll get exactly the right answers. The weakness of the frequentist argument or approach is that, as I said, it's not only random, but it's stupid, right? We know that for the die, it may not be exactly a 6, it'll be close to a 6, and the frequentist approach has no way of taking that into account. The Bayesian approach does. Now I see there are 2 more comments here, so let me try to answer them quickly. From Jessica, it's assumed that S is either finite or countably infinite. This is true. Thank you, Jessica. I glossed over that point. Yes, S is either finite or countably infinite, meaning that it may be mapped onto the real numbers or pairs of real numbers. That's important for the axioms to hold, and for some of the more formal aspects of statistics that I will not go into in these lectures. And then going back to Pranjal, is it right that we wouldn't mean that all frequentist probability is superior given that it makes no such assumption? Yes, frequentists feel it is the superior way because there's no bias in the method, no bias coming from assumptions and no bias from the method itself. However, as I said, if you needed to know the answer to 1 part in a million, you would have to throw the die 10 to the 12th times, and that's impractical. Okay, so in certain well-controlled situations, a Bayesian approach is considered superior, but the Bayesian approach occupies a position sort of halfway between the classical approach, which assumes too much, and the frequentist approach, which makes no use of prior information. And you know, I think on Thursday, we will definitely talk about Bayesian methods. So thanks a lot for those questions and comments. I appreciate it. Okay, so I want to move on to something that appears in all probability problems. That's the question of conditional probability. You know, we're not here just to play card games. We do want to understand complicated things like, you know, if we have an event B that already occurred, what is the probability that A subsequently occurred, given that B already occurred? And so this part here in the notation, that is the correct notation for saying we want the probability that the event A occurs given that B already occurred. This is known as the conditional probability for A given B. Okay, so this drawing gives you a little bit of a picture, right? This, this red part here is the set of events or the subspace, the subset of the sample space S which pertains to B. A is some different subspace, in blue. And so the part that we're asking about is this part here, the overlap. And we want to know if we are in subspace B, what is the probability that then upon having determined that we're in B, we are also determined in A intersect B. That's the conditional probability. All right, so I have two more questions. Hi, Miko. Does it mean that quantum mechanics is sort of a frequentist theory? So it turns out that quantum mechanics is a whole different beast, okay, because it's intrinsically random. I think everybody here knows that that's the key feature of quantum mechanics is its randomness. But remember, quantum mechanics describes phenomenon, and we're talking about ways of addressing data from an experiment. So in a way, they are different aspects. They both are random. I would say that maybe in a certain sense, quantum mechanics is frequentist because it doesn't assume anything about itself and it doesn't take prior knowledge, right? It's usually not deterministic, but it really is something outside the scope of these lectures. And then going to Neural, you're asking whether A and B occur in the same experiment, not that B occurs in one. Yes. So generally speaking, we're talking about that the sample space here corresponds to a particular experiment. Maybe it to be concrete. B is that a neutrino interacted. A is that a muon track is observed. And so A intersect B would be that a muon track appears in a neutrino detector given that a neutrino interacted. Okay, great. So the probability of that intersection will depend on the probability that B occurs, right? Just this B of P here, and necessarily excludes or eliminates a big part here of the sample space. That's gone once we consider P of B. So to write down the answer, it turns out the probability that A occurs given B is the probability of the subspace which is common to A and B here, A intersect B, divided by the probability of B. Okay, so in some sense, it's a little like taking B here, this red region, as a subspace of its own. This is a subspace of its own, call it S prime instead of B. And now we're looking at this sub-event, which is a subspace of SB, and asking what's the probability of that. And so the reason why you need to find to divide by P of B here is because P of B is not 1, but the probability would only make sense once you've normalized to that. And another way of seeing it, that we need this term in the denominator, if we just set A equal to B, then B intersect B is B, the probability of B that occurs, that B, given that B did occur, has to be unity. So this only works out if we have this part in the denominator to take care of the fact that B already occurred. Okay, so this is the important point I want to make. Of course, it's trivial just to multiply through and write this way. And this equation here in the box is the starting point for conditional probabilities, and in particular for Bayesian statistics. Okay, good. So how do we calculate this? This is a different kind of diagram. You can see I simply rewrote that law from here, the box. I just rewrote it, whoops, here at the top. I said, let's begin with nothing. Maybe we get B, or maybe we don't get B. If we get B, then we can see if we get A. There we are, we got A up here. Or maybe we didn't get A here. This is clearly the probability to get B and A, right? Because that's what happened. We got B and then we got A. Below it is the probability to get B and anti-A, or the complement of A, so on and so forth. So this is just a kind of logical diagram to show that indeed this makes sense viewed as a kind of sequence. Okay. Now, I'm going to skip this. It just says that you can break the sample space down into non-overlapping spaces here. And then it allows us to write a sum rule here, ultimately here, for probability of A in terms of B and the complement of B. All right? But it's straightforward. So I like to move rather than getting lost in lots of set notation and so on. I'd like to give you a concrete example of, conditional probability, and this has a point to it. It's not just an illustration. So let's imagine we know a guy named Tom, and he lives in a place of the world where the a priori probability that someone has Ebola is 0.1%. Okay, so it's small, but not negligibly small. And then he's tested for Ebola, okay? And so he wants to know, given the outcome of his test, does he have Ebola or not? All right, kind of a big question. All right, so this first piece of information is probability of Ebola is 10 to the minus 3, which means the probability of not having Ebola is 1 minus that, 0.999. Okay. So this just repeats that. Now, the test that he's taken is a good one. And what that means is that if he has Ebola, the test is positive for Ebola 98% of the time. It gives a negative, a false negative, 2% of the time. So this is a good test because most of the time the outcome corresponds to having Ebola or not having Ebola. Okay, and then similarly, if you don't have Ebola, the chance that it gives you a negative reading is again very good, 0.97, which means the chance that you get a false positive here when there's no Ebola is only 3%. So we have now the information needed to calculate or inform Tom what is the probability that he actually has Ebola. Now, what do you think? Do you think the probability after taking the test and saying that the test is positive is this number, 0.001? Let's see. Okay, so we want to know this quantity. We want to know the probability, given that the test is positive, that he has Ebola. That's not the same thing as this. This is the probability that if he has Ebola, the test gives a positive reading. That's 0.98. That's not the same thing as this, and that's a really important point. So let's go ahead and do the calculation. According to the definition of conditional probability, this probability, the one that we want, can be written this way. Problem is we need to calculate the numerator and denominator. So again, from probability, we know that a conditional probability, the probability that he both gets a positive reading and has Ebola is this expression here. The denominator we can write is that the probability that he gets a positive reading is the sum of the probabilities for getting a positive reading when he has Ebola and the probability of getting a positive reading and not having Ebola. Okay, so we can put the pieces together. These are the pieces here. It's really pretty straightforward. You plug the numbers in, and the answer that you get is that the probability that he has Ebola is 3.2%. Okay, so should he be happy? What do you think? Do you think it should be happy? 3.2% is a small number, right? So maybe you say, this test stinks because he got a positive value, but actually the chance he has Ebola is only 3.2%. So it's a lousy test. But that's wrong, okay? Because the test told you something. The prior probability was 0.001, was 0.1%, right? And that jumped up to 3.2% as a consequence of the information that the test came out positive. Now, the other thing that I want to emphasize, so whether he worries or not is a different question. It's certainly worse than getting 0.001. On the other hand, 3.2% is not a very high chance of having Ebola. And so he's most likely going to be okay. Now, one thing, again, I want to emphasize, because this is a common thing that people make a mistake. The probability to have Ebola with a positive test result is not the same as the probability to have a positive test result when you have Ebola, right? The number on the right-hand side is 0.98, and the zip problem on the 0 side is 0.032. Okay, so don't ever make this mistake. It's called probability inversion. Scientists make this mistake sometimes, and other people like science writers make this mistake all the time, and the general public does. So there are nasty corporations out there who want to take your money because they think you can't tell the difference here between the left hand and the right hand side. Be smart and don't make the mistake of probability inversion. All right, so we have a question from Edward, a comment from Edward. Thanks, Ed. Edward's pointing out that we need to test again and updating the priors based on the results. So yes and no. It depends, Ed, on whether the positive outcome here, whether that positive outcome is random or not. Let's say that it's not 100% because there's some feature of Tom's blood that prevents it from registering the presence of Ebola virus. So in that case, his blood's not going to change just because you test again, in which case you wouldn't be learning anything new. But if the fact that he got a false positive or false negative really was a random thing, stochastic thing, then yes, you would be right. You would want to take the 3.2% as a new prior instead of the 0.001, obtain another test, and reevaluate the probability. Now, of course, it could turn out that the test is negative, and that would seem to confirm that he actually doesn't have Ebola. All right, so let me move along. Independent events have everything to do with conditional probabilities. It can happen that the probability to obtain event A is independent of B, right? It's just the probability of A. In that case, you can go back to the rule that we had. The probability of A intersect B is just the product of the probabilities. And this means that they, A and B are independent. Okay, so two things being independent is rather special in science. It doesn't happen all the time. People sometimes assume that it's true when they do data analysis, but you have to be careful and make sure you know what you're doing. Okay. All right, so I want to move along and introduce some other concepts. I think a random variable is probably clear to everybody, right? So you have, let's say, in your sample space, an elemental event. Which elemental event you'll end up with as an outcome to an experiment is a random thing, but you might, as a mathematician or a physicist, decide to attach to an elemental event a particular real number or integer number, x, so that the way you quantify or specify the outcome is by giving the value of x. Okay, so in other words, for tossing a coin, I can say it's a heads or a tails, or I could say, well, when it's heads, I'm going to write down a 1, and when it's tails, I'm going to write down a 0. And then I toss the coin, I say the outcome is +1, because that's how I specify getting the heads. In that case, that variable x is now a random or stochastic variable. And this is important whenever you want to do this. This is the basis, of course, for doing any kind of quantitative analysis. So here's a simple example. I toss 2 coins, fair coins, meaning that they're not trick coins. We don't pay attention to which is which. We count up the number of heads. And so you would get this table here of random outcomes. X is either 2 or 1 or 0. Okay, or maybe we want to say X is an exclusive OR function, and then it's 0 or 1, depending on the outcome. All right, so now we have, for elemental event E sub I, we have a random variable x, whose value could be x sub k. Let me zoom in a little bit so it's easier to see, which is a map for probability onto a function f, which is a function over the real numbers. Okay, so that probability function, that function f, is what we call a probability density function, sometimes called a mass function. And it has 2 restrictions. First of all, it can never be negative because by the axioms of Kolmogorov, we all agree that probabilities cannot be negative. And also the sum of the probability of all possible outcomes has to be unity, because if you do the experiment, something has to happen, right? That's what this says. And that sum can be discrete over discrete variables, like here with the coins, or it can be actually a real number. Right? So if we look here at this example of the coins, and we're counting the number of heads, this is the domain of the function f, either 2 or 1 or 0. And this shows you here the probabilities of getting 0 is 1/4. The probability of getting a 1 for x is 1/2. The probability of getting a 2 is 1/4. And so f is the PDF for x. X is the random variable associated with the outcomes, one head, one tail, etc. For a continuous variable, there's a little bit of a subtlety here because we can't say what is the probability to get one value on the real number line. That's just not possible. But we can ask, if we pick a value x, what is the probability to get a value in the neighborhood of x, or between x and x plus dx? And in fact, that's what, for a continuous variable x, that's what the PDF, the probability density function, means. F of x dx is the probability to observe a value for the stochastic variable x in the interval between x and x plus dx. Okay? A histogram is an example of this, right? So if you take the bins of this histogram here, one of the bins, then the height of the histogram gives you in relative terms the probability to get an x in that bin. So histograms are very much a kind of practical representation of a PDF for a continuous variable. Okay. Are there any questions at this point? Looking at the webinar chat. Okay, great. So let me continue. If we could only work with a single real variable, everything would be pretty easy and this lecture would be over. But that's not the case, right? Neutrino events, neutrino phenomena, things like cross sections and so on, depend on many, many different quantities. And in fact, you often observe many quantities. So we have to somehow graduate from a single variable like x to something more complicated. For example, if we consider that muon that's produced in a charge current interaction in a neutrino detector, we're probably going to want to measure the 3-vector of that particle's position, or maybe its kinetic energy, or in some other context, angular momentum. So we now want to consider the joint distributions, the joint PDFs, for multiple quantities at the same time, okay? And it's important to understand that even if the quantities are something weird, like the length and color of a fox's tail, the different components are somewhat independent. They're not trivially a function of each other like here. Okay, so writing x as p for the momentum and p squared for the momentum squared, this is not the case because one is a simple function of the other. All these other cases here tell you legitimately independent observable quantities, okay? All right, so if we have, say, x and y as two random variables defined over some sample space, then again, the two-dimensional function has to be non-negative, and ultimately integrating over the entire sample space, it has to integrate to unity. And here's just a depiction. We've got x horizontally, we've got y on the other axis, and then vertically is the function f of x and y, just shown here as we represent it as a surface, okay? So if we now pick out part of this xy plane and call that event A, and then integrate over A, we have the probability of A. That would in some sense be the volume under some patch that I choose here to be event A. What's the volume? The volume of the whole thing is unity. What's the volume of the patch that I'm calling A? And that would be then the probability of getting A, okay? This is just another picture of the same thing. Let me move on. Okay, so having now established that we can work with two-dimensional PDFs, let me now collapse this, which may seem perverse given that I introduced it, but there's a really important concept here that I make sure that I get across. So it could be that maybe you don't care about one of the variables, y. And then in order to not care about a variable, what would you do? If you think about it, you realize that you're going to integrate it out, right? Theorists like to talk about that. We integrated out the heavy degrees of freedom because we don't care about those details. In the context of statistical physics, or statistical methods, I should say, if you have a two-dimensional distribution, even a complicated one, but you've decided that you're only interested in X, then you integrate over Y, leaving you a PDF, a valid PDF that has all the properties a PDF should have, which is only a function of X. This is known as the marginal distribution for X. And of course, you can also form a marginal distribution for Y, which is a different function. Obviously, they're not going to be the same. And in general, this 2D PDF here is not simply the product of these marginal distributions. Okay. So let's go back to conditional probability. In this case, let A now be that we've got a X in some range, and B is that we have a Y in some range. So this is X and this is Y. Then A corresponds to a vertical strip like this, and B corresponds to some horizontal strip like this. The conditional probability for Y given X would mean that we are now, let me blow this up a little bit, we are now in here in this red part. Okay, that's A intersect B, and therefore that's relating to the probability for A intersect B, right? So given what we know, you can work out that the conditional probability for Y given X is the joint probability up here divided by the marginal, because the A event is where we integrate over Y. That means we can have any Y that may occur. So you end up with this expression here. So this is the conditional probability for continuous variables for Y given X. It is not, as you can see by inspection, the probability for X and Y, because that's just the probability to be sitting someplace in the point. We've restricted ourselves to event A. Therefore, we have to normalize by that probability for A. All right, therefore, we're really reducing it to a one-dimensional problem, right? We're sticking ourselves in this blue vertical band and asking what's the probability to land, excuse me, in the small red square. And that's what this expression tells us. So this conditional PDF and the marginal PDF are very different things, and you should never confuse them, even though it's very easy to confuse them. We can play the game the other way. What is the probability to get X given Y? It's still the same. This is still the same red part, but we're now saying first we want to restrict ourselves to the horizontal black band, and then ask what is the probability to land in the red part. And so we can express this a different way in terms of the Y's. And so we actually find that we have two different ways of re-expressing the two-dimensional PDF in terms of a conditional and a marginal distribution for Y in terms of X, or for X in terms of Y. Okay, so again, the marginal distributions are not equal to the conditional PDFs. As an illustration, we could look at this. I'll ask you to look at that on your own. I want to move forward. Well, maybe I can move forward a little bit. Now, let me move forward. This is just a simple illustration that gives you an immediate visceral feeling for the difference between the marginal distributions here and the conditional distributions here that are obviously by inspection not at all the same. Okay, so now suppose as a special case, we have that this two-dimensional PDF can be written as a special case as a product of two functions, one that is purely a function of X and one that is purely a function of Y. So that the X and Y dependence of our PDF factorizes, right? That is not the case in this example I skipped over. This cannot be written as a product of a function of X and a function of Y. Okay. If, however, you can do it that way, then you can show that F1 actually is the marginal distribution of X, and F2 turns out to be the marginal distribution of Y. Okay, similarly, it turns out when you do the math that the conditional probability of Y given X is F2, and the conditional probability of X given Y is F1, and that this conditional probability doesn't depend on X, okay, because it's only a function of Y. This probability, this probability to get X given Y depends only on X, doesn't depend on Y at all. So that means that we get the same PDF for X no matter what Y value we take. And that is, of course, the definition, the meaning of independent. Okay, so when G of X given Y is independent of Y, and H of Y given X is independent of X, this just says that X and Y are independent variables. And this is a definition. Okay, this is important. All right, so here is the distribution. It shows, it's real data showing people's weight in kilograms scattered against their height in centimeters. So maybe I can ask the class, all 68 of you to vote, are the weight and height independent variables or not? So let's take a minute and use the window, the participant window to vote. I hope, Doyle and Evan, that works. Does that functionality work here?
There is a way to do a poll.
Go ahead. Ethan can comment.
It doesn't see, I'm not seeing votes appear, so maybe.
We can do a poll, but we have to set the questions up beforehand.
Oh, okay, sorry, my apologies. So in a simpler version, raise your hands from Jessica. Cool, let's do that. Oh, what's the capital F? I'll go back to that in a second, Sheldon. So can we do a vote by hands? Let's see. If we do grid video.
We don't need video. You should be able to see a count on the participant list.
Look at participants.
Okay, so I see, there we go. That looks like it's working nicely. All right, so one person says yes. The question is, are they independent? So raise your hand if you think they are independent with no dependence. Okay, so raise your hand if you think they are dependent. Okay, lots of people. All right, great. So this is obvious to all of you that they are dependent, right? And it should be obvious because imagine that I picked a height between 160 and 165 and then considered what the weights are. Well, pretty clearly, I'm going to end up with weights mainly in the range of 50 to 7 kilograms. But if I then change my choice and say I want to take tall people, or between 185 and 190, for me that's tall, now I'm going to get weights over here that are more like 80, 90, even 100 kilograms. And so the PDF for the weight depends on which heights I'm selecting. So they depend, they're not independent. All right, let me answer Cholong Lee's question about F, capital F. She's asking, or he's asking about these. And these are the cumulative distribution functions. So I eliminated from the lectures because I only have time for 3 lectures, but let me just quickly define here. F of X is by definition the integral. Let's say we have a PDF of X and it's a continuous variable. So we're going to integrate over that PDF out to infinity, whatever is the maximum allowed value of X prime. And we're going to start at X. Okay, this is the cumulative PDF. So it's, wait a minute, no, sorry, it's not that. I've now got myself confused. So it is the other way around. Sorry. It's the integral from minus infinity to X. Okay, so if you have a PDF that looks like this, that's f of x, this is x, then the cumulative, the CDF, cumulative density function, is basically the area under the curve up to that point. Okay, and so this bottom statement here is just saying if the PDFs factorize, then the CDFs factorize as well. It's not really such an important point. Okay. All right, but thank you for asking. All right, good. So I'd like to switch gears now. I think we've CDF factorize and PDF also factorize. Yes, it's a necessary and sufficient condition. Okay, so I'd like to switch gears and talk about something else. Let's say we're all comfortable and we have our PDF. There it is. And x is a random variable. So we define the expectation value of x, that random variable, according to this expression. Okay, and there are different ways of looking at this. If we integrate from minus infinity to infinity of f of x by itself, this turns out to be super boring because always, 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 no matter what f of x is, the integral of f of x dx over the entire range of x is just unity, because it's just saying that something had to happen. Some particular x had to show up when you sampled that PDF f of x. But that's not what this is here. It has that all important x in front. And so this is the expectation value of capital X. It's in a way the average value for x given the shape of f of x, right? So sometimes people say it's like a weighted mean of x. Okay, and in fact, we call it the mean of x, and it's often denoted in this kind of work by the Greek letter mu. Okay, so if the PDF is more or less concentrated in some region on the x-axis, okay, so here's x. If the PDF kind of looks like this, well, the mean is going to be in here someplace, right? The mean is going to be, I don't know exactly where, but it's going to be in the middle, okay? And so in some sense, the mean gives a characteristic value. If this is 0 and this is 100, we know that 52 is a characteristic value of f. And we would not say 2,000,005, and we would not see minus 52. All right, we would see for f of x a value that's sort of close to the mean, whatever the mean is. Okay, so here's a picture. It's a summary statistic. It doesn't tell you about the shape of f. It doesn't tell you that it has this little toe out here, this little tail or anything like that. But it does kind of tell you something about the distribution, a typical value for the distribution. Okay. Now, what about the variations? We pull one value of x out according to the PDF f of x. We pull out another value, and a third and a fourth. How much are these values going to jump around? Well, that's answered by the variance. So let's just kind of reason this through. Here's a funny kind of distribution. It's centered on 0. So if it's centered on 0, then the mean is 0. So we're going to say for this page only that mu is 0, the mean is 0, and calculate the expectation value of x squared instead of x. All right, the expectation value of x is 0. You can just, that's just shown explicitly here. The expectation value of x squared is calculated here, and it's a squared. So that's because I have two delta functions, one at minus a and one at plus a, and they're supposed to be centered on 0. Diagram's a little bit imperfect. All right, so that means that if we have a very large, like 700, then the expectation value of x squared is going to be very large. If a is small, like 10 to the minus 3, then the expectation value of x squared is also small. So how spread apart this is relates to e of x squared. Okay? Now, suppose mu is not equal to 0. Well, we could just shift it with a new variable by subtracting mu off and do this same kind of calculation we're talking here. Here's a calculation that's a little bit more involved, slightly more involved, but the bottom line is that the expectation value of x minus mu, right? Expectation value of x minus the mean quantity squared turns out to be the expectation value of x squared minus mu squared, and that's always 0, greater than or equal to 0. It's only equal to 0, in fact, if your PDF is just a delta function at 0, which is very boring, so we won't worry about that. Okay, so again, this expectation value tells you something about how spread out things are, and you can see a way of calculating, basically subtracting off the mean so that it only pertains to how spread out it is. Okay, so this quantity is known as the variance. It's called the variance. It's written as sigma squared. Mu is the mean, sigma squared is the variance, and for various reasons we often talk about the root mean square, the RMS, or sometimes called the standard deviation. That's what I like to call it, or SD for short. Okay, so we now have two things, that summary statistics that we get for our PDF, whatever it is. One of them is the mean, the other is the standard deviation. And so we can define, is common and useful to define a standardized random variate, which is x minus mu, so the numerator has expectation value 0, and then we divide by sigma so that the variance of this combination ends up being 1. All right, so the mean of u is 1, and the variance of the standardized random variate u is also 1. Okay, all right. So to summarize, the mean tells you where things are, like in the drawing, and the standard deviation tells you, or the variance tells you, how spread out it is compared to the mean. Okay. We can do the same thing in more than one dimension, right? So now we go back to our two-dimensional PDF. We can have an arbitrary function h of those two random variables. We can calculate the mean of h by integrating with respect to a PDF for h. We can also express the dependence on x, y by going back to the PDF and x and y. That gives us the mean of h. And we can also get the variance in the same way. So there's nothing special about the fact of having more than one dimension. You can just as easily get a mean and a variance that way. Okay. One thing is maybe a little bit important is that mu of h is not necessarily the value of h at the mean of x and y. Sometimes it is, but you cannot assume that it is. And this page 46 just shows you a little bit of an example for that. Okay. Now, let's think about what we could summarize in terms of a two-dimensional PDF, right? Think back to that picture. Maybe I can find it quickly. That picture, where is it? Here it is. Think about this picture here where we've got x going to the right, y going backwards, and here's our f of x and y. We want to now characterize and summarize the properties of this function in terms of our summary statistics that we know already, okay? So we just kind of follow our nose and write down what we know. We can take the mu, the mean of x. We can take the mean of y. We can take the variance of x, and we can take the variance of y. And you would say, oh, okay, I'm done. But it turns out that when you have two dimensions like this, there's an extra fifth expectation value, where instead of having, e of x minus mu sub x squared, instead of having that, we actually have the expectation value of x minus its mean times y minus its mean. So you kind of mix it up. It's like a cross term in a way, right? Written out explicitly for comparison to these ones up here. Now, this is not the variance, because the variance really pertains just to one unique variable. This is the covariance of x and y, and it's donated by sigma squared sub xy, compared to sigma squared sub x or sigma squared sub y. All right, so this tells you something about x and y taken together. Okay, now it should be obvious from the definition. Let's look at the definition. The integrand is completely positive. Integrand is completely positive here and here. So from the definition, the variances must be positive. But it turns out the covariance can be and often is negative. Okay, and we'll understand that in a second. That's actually a very important feature of the covariance. So the covariance is sensitive to the way x and y change together in a coordinated way. Just consider this product here that's in the middle. If y increases when x does, compared to the mean, then the product will tend to be positive. And if x decreases, however, when x increases, then the product will tend to be negative. Okay, so that means that the product here can be both positive or negative. It's positive when x and y increase together, and it's negative when x goes up and y goes down at the same time. Okay, so here's an example or a depiction. X and y on the plot on the left, you can see, if you think of this as representing that hill, that shape that I had before, then it shows that, yeah, y, when x goes up, moves to the right, y goes up, it moves upward. Okay, here, however, when x goes to the right, increases, y decreases, it goes down. So in the case of the left, the covariance is positive. In the case on the right, the covariance is negative. Okay? All right. Now you could, of course, have the borderline case where sigma squared xy turns out to be 0. It's neither positive nor negative, it's 0. It doesn't mean, nonetheless, that x and y are independent, right? When I say this, you kind of probably immediately have in mind a picture where we have some ellipsoid or ellipse, which is like that. And, it seems that x and y are independent. This does give you sigma squared xy equals 0. And so in a sense, yes, the fact that they're independent here does lead to the covariance being 0. But you cannot run it the other way and saying that x squared xy being 0 means that the two variables x and y are independent. Okay, why? Well, look at this example. Okay, so this one, they're independent. Okay, and sigma squared xy equals 0. Sigma squared xy for this guy is also 0, but they're not independent. This shape cannot be expressed as a product of a function of x and a product of a function of y. It's also true that if I take a slice of x here and I take a slice here, I will get different PDFs for y. So these are not independent. This is independent, but in both cases, the covariance is 0. Okay. All right. Now, one of the problems, let's say technical problems of dealing with the covariance or the variance for that matter, is that they're big or small, but they're big or small depending on what kind of units you use. I mean, are sigmas measured in kiloparsecs or are they measured in Fermis? Depends on the problem. And so just looking at the value for sigma squared xy by itself doesn't tell you if two variables are correlated or not. It only tells you something if you compare to the variances, right? So the variances are measured in meters and your covariance is in millimeters. Yeah, that's a small covariance. But if everything is measured in millimeters, maybe it's not a small covariance. So the way we take care of this is to define the correlation coefficient by the equation in the box. And that's just taking the covariance and normalizing to the product of the standard deviations. This is dimensionless. That's a good sign that it's a useful quantity. And it turns out that it is bounded by -1 and 1. The correlation coefficient can never be larger than 1 or less than -1. And if positive, and it's close to 1, then you have a strong positive correlation, okay? If it's negative and close to -1, you have a negative correlation. And if the correlation coefficient is essentially 0, then you have two variables, x and y, which are basically uncorrelated. Okay. All right, good. So I'd like now to go ahead and organize this information in a matrix. Here's the covariance matrix. We're going to use this in tomorrow's lecture. So you basically, the diagonal elements are the covariances, are the variances, and the off diagonal elements are the covariances. All right, of course, if the covariances are 0, then this is a diagonal matrix and there's not much point in writing it down. It's useful when the off diagonal elements of covariances are not 0. Notice that the determinant of this matrix can be written in the simple form involving the correlation coefficient. If the correlation coefficient actually achieves the value 1 or -1, the determinant is 0, and that's bad news because we often have to work with the inverse of this covariance matrix. Okay. Now, in the lectures, I'll deal with 2x2 matrices, but this is an important part of machine learning as well. And in fact, these matrices can be literally 10 million by 10 million. And in that case, you need special techniques to invert these covariance matrices. They're often sparse, meaning that many of the elements are 0. Okay. So, it's already 3:04, so I have about, what, 10 minutes left, Andre?
Yeah, that's right, 10 minutes, yeah.
Okay, so I want to just introduce 2 or 3 common PDFs to all of you students. Sorry, I missed a question. Dehang, thank you very much for your question. What does it mean if X and Y are dependent but uncorrelated? So it means that you have, well, let me give you another example. I'm going to insert a blank sheet here. There we go, there's a blank sheet. Sorry that it's vertical, but you can still see it. So let's take the case when we have, oops, come on, Michael, all right. We have an x-axis and a y-axis, there we go. And then the kind of distribution we have in x and y turns out to be like a ring. Okay, so this is my, oh boy, I'm terrible. I'm trying to draw a uniform ring, but let's say that in terms of x and y, their values are for some reason restricted to this ring. Okay. Now, I'm sure you can see that the covariance of this guy will be 0, okay, which means that the correlation coefficient will also be 0. But clearly, there's a strong interdependence of x and y. When x is large, y is small. When y is large, x is small. Okay, in fact, there's also a stronger correlation because roughly speaking, x squared plus y squared is a constant in some sense. Okay, so this is an example where they are strongly dependent on each other, but they're uncorrelated in the sense that the covariance or the correlation coefficient is 0. All right, so that's what I'm trying to say, that you have to be careful when you get these results here. It does not mean that x and y correspond to some simple ellipse in the plane. Okay, you're welcome. Adrian asks, any more sophisticated objects that can tell us about those non-trivial dependencies? Wonderful question. Student has never asked that question before. It's great that you asked that. So it turns out, no. I'm only going to talk about the first and second moment because time is short. There are other moments like the kurtosis and the skewness and so on. And some of those can inform you a little bit about there being additional structure to multidimensional PDFs. But basically, once you care or need to know about the structure, which in modern cases is what we do, then you don't want to rely on simple summary statistics like this. Summary statistics are integral quantities and will only take you so far. If you need to know additional things, then you should move away from summary statistics and look explicitly at the interdependence of the individual variables. Okay. Next question. So maybe we can say independent is much stronger claim than uncorrelated. Absolutely yes. Zhusheng, you absolutely got the point. So uncorrelated is a little bit loose. Independent is a really strong statement. It actually rarely shows up in at least in experimental science. Okay, so you absolutely got the point. And Yikong, yes, there are other summary statistics. As I said, there's the skewness. The skewness tells you if you have something that's a bump, it tells you is it symmetric or does it tend to have a tail to one side? Then it's skewed, right? This would be skewed positive. It was skewed on the other side, be skewed negative. And then finally, let's see, oops, sorry. I didn't mean to do that. I wanted to erase something. Let me make a little space down here. The fourth moment is known as the kurtosis. It's a Greek word meaning heavy tail. And what it says is that compared to a Gaussian, this is meant to be a Gaussian distribution. You can have distributions, for example, like a Breit-Wigner or Cauchy distribution, which is much more sharp at the peak and much slower to fall off to zero. That's a Cauchy distribution, and it has a large kurtosis. So kurtosis tells you whether the tails out here are really large or not. Generally, in scientific work, we don't care so much unless you're looking for very rare phenomena that corresponds to the tail. But if you're in the stock market, you care everything about the tails because those are the major events that make you win or lose money. Okay, so let me try to take just a few minutes. You can look at the notes. I wanted to tell you about 3 or 4 simple PDFs. There are a lot of slides here, so I'm going to go through really fast, but they're kind of straightforward and you can look at them on your own or we can talk about them in the discussion. Okay. Mitra Jyoti, if X and Y are dependent, could we in principle have a single distribution function? If yes, how would we construct that function? So I'm not sure I know what you mean. We can have a single distribution function for anything that is probabilistic. So by construction, yes. Doesn't mean you can write down a nice functional form for it, but you can construct it just by collecting data. Okay, that's an important topic that maybe I can talk about on the last day. All right, so the most important PDF corresponds to a Bernoulli trial. It has to do with success or failure, where in this case, maybe success is you pick out of a basket a red ball and then picking out a white ball would be considered failure. And, you know, there are different ways to talk about this. The important thing is that it depends on one and only one parameter, P. That's the probability to get the red ball, you know, success. And then the only other alternative is to not get a red ball. And so the probability for that is 1 minus P, okay? It's easy to show that this probability P is the mean of the Bernoulli distribution. And you can also calculate the variance as being P times 1 minus P or P times Q. Okay. I'm going to skip all of this. It just shows you what is the functional form of the binomial distribution. It depends on P and Q. Remember, Q is 1 minus P. If R is the number of red balls that you got and N is the number of balls you pulled out of the basket, then it's P to the R, 1 minus P to the N minus R. So the number of failures, so the probability of failure to the number of failures times the number of, the number of successes raised to the number of successes power times the number of failures raised to the number of failures power. And then this binomial term here, this which is well known to all of you, is just a normalizing factor, okay? I like to point out when I teach my students that in the West, we call this the Pascal Triangle. But if you look in history, there's a famous Chinese mathematician, Yang Wei, who found this at least 300 years before Pascal wrote it down. And if you know Chinese, or even if you don't, you can stare at this and interpret it as Pascal's triangle. Pascal's triangle is just a construction for getting these binomial terms there. So bravo to the ancient Chinese. All right, anyway, I want to move on. These are distributions, examples of binomial distribution. The blue ones here have a relatively low value for p of 0.1. The red has a value of 0.5. The green has a p-value, probability value of 0.9. So you can see that the mean does correlate with the value of p. Okay. All right. Poisson distribution can be derived from the binomial distribution. Again, I don't have time to go through this derivation. This is the formula for the Poisson distribution, where R is the number observed, such as the number of students who have signed on to this lecture, and lambda is the expected number. It's the single parameter for the Poisson distribution, and that would be 65, since the number of students who attend these wonderful TASI lectures tends to be 65. Okay, so again, there's a mean and a variance, and the distribution looks a lot like a binomial distribution extending to very large values. Okay, so I'm sorry that I can't go through this more carefully, but I'll be happy to do it another time. The normal distribution, everybody knows a normal or Gaussian distribution. It depends on two variables, the mean and the standard deviation, or RMS. The variances are determined exactly by that. That's where the notation comes from in the first place, is from the Gaussian distribution. Of course, you know what this looks like. Here are three examples due to a very nice book by Luca Lista. The larger the variance is, the broader the Gaussian is. Of course, you can shift the peak position or the mean position from 0 or 1 or 2. All three of these curves are normalized to unity. Okay. Okay, let me just finish making a couple of more points about the Gaussian distribution, and then I think I'll pause for questions and discussion. Let's go back and look at the expression because it went by kind of quickly. Let me get rid of this green stuff. Notice this argument here, x minus mu over sigma. If you remember, I talked about a standardized variate or standardized variable, and I wrote it as x minus mu over sigma. So you can see that this standardized variate is nothing more than the business part of the Gaussian. Okay, so if we come over here, that's what I've done. For historical reasons, I use the letter z instead of u, but of course it's the same quantity. So a Gaussian is really e to the minus z squared over 2 with some normalizing coefficient in front. It's a very simple function, one that mathematicians like. You can also calculate the cumulative distribution function, which I defined before, from this, and that defines actually the error function, which is a mathematical transcendental function defined by mathematicians. Okay, now this is important. It's very important because later on when we consider hypothesis testing, we'll want to know, let's go back to the picture, how likely is it for this guy, this light blue one, that I get a value of 0.5 or that I get a value of 3.5 or -2 or something like that? Or what's the probability to get -2 or something more negative than -2? We'll really want to know that when we consider hypothesis testing. And it's traditional to relate these things back to the Gaussian distribution. Okay, so the probability to obtain z greater than 3 would be 1 minus 1/2, 1 minus 0.9973. Okay, because this is the probability to get z greater than 3 or less than -3. That's what this quantity is. But I'm only looking at one of the tails, so I want 1/2 of that. Okay, sorry, without the 1 minus. Okay. Now, one of the reasons why the Gaussian and normal distribution is so well known is that many other distributions asymptotically look like it. So the binomial distribution, if we go back to the picture, this red one kind of looks like a Gaussian, doesn't it, right? And in fact, you can almost treat it like a Gaussian by defining a random variate z, which is x minus the mean, divided by the standard deviation for a binomial, okay? Or here's a Poisson distribution. Okay, what is the probability to get x in the range between A and B, where this is the mean and this is the standard deviation, okay? You can relate these things to the Gaussian as an approximation, right? As an approximation, true only in the limit, and it turns out that it works very well. So here's the Poisson distribution for several values of mu. The blue lines are the Gaussian approximation. You can see once you get mu greater than about 10, the Gaussian approximation looks very well, okay? There's also something known as the chi-squared distribution. Maybe I will come back to that later, but unless, well, or I could go over it now. But I really, since you asked so many great questions, I'd like to reserve time now, the next 10 or 15 minutes for discussion and questions. So thank you, and let's, I'm looking at the chat window. Please let me know what your questions are.
All right, thank you. So again, you can write your questions in the chat, or you can raise your hand if you have more questions. Or everybody's very, very happy.
There were really wonderful questions during the lectures. What I could do, Andre, if nobody has a new question, I could take 3 or 4 minutes just to explain the chi-square distribution, since we'll refer to that in the next lecture.
Sounds good. Oh, somebody wrote something.
Ah, great. Adrian Thompson, again, thanks, Adrian, for your questions. So yes, I will talk about combining data from 2 sample spaces. Well, two sample spaces, I would say. Yeah, okay, I see what you mean by coherent and sevens being 2 different sample spaces. So yes, we will talk about combining measurements. That is an important topic. It will be based on, we'll do a least squares treatment of this. And the least squares treatment is also relating to this chi-square distribution. So if there are no other questions, or requests for material, then I will take 2 or 3 minutes to talk about the chi-squared PDF. Yep, good, another question. Will we also talk about the median expected significance and p-value? So p-values, I sort of just went over. Let me talk about p-values now. Again, I'll introduce a new page, whoops, and draw on it. Okay, so here's an independent variable x, and this is the axis for the PDF. All right, so this is f of x, and this is x. And so let's suppose we have a PDF, which is roughly Gaussian shaped, although it doesn't have to be Gaussian shaped. And so this is a PDF, right? So the integral of the PDF across the x-axis is unity, right, is 1. But maybe the value that you observed in your experiment is out here. Okay, so this is x observed, right? And you know, the mean is here someplace, and the variance corresponds to this width, or the standard deviation corresponds to that width. So this x observed is pretty far away from the mean. And in the context of doing scientific observations, you may say, well, I got an unusual value for x when I did my experiment. How unusual is it? How unusual is that value for x? And the way people answer that question is by saying, well, the probability to get that value of x or something even more unusual, in this case, something higher, any of these values going out to infinity, the probability of obtaining that value of x or anything larger is the probability of this tail. So this is known as the tail probability. Okay, and the other name for the tail probability is the p-value. Okay, so tail probability is kind of a general term that you use whenever you're talking about the tail of a PDF. The p-value shows up specifically when you're asking what is the likelihood or the probability of something happening. And usually you are interested in things being unusual, not being usual. Okay, so for example, let's say I toss a coin 100 times because I'm really bored. And I count the number of heads. And I would expect for most coins to get something like 50 heads. If I get 57, yeah, that's typical. If I get 44, a little unusual, but it's okay. But if I observe 82 heads, for an ordinary coin I picked off the street, that's a really surprising value. And you'd say, well, either there's something wrong with the coin, or I was somehow really lucky in some sense of getting 82 heads when I really expected between, 35 and 75, something like that. Okay, so the p-value would tell you how unlikely it is to get 82 heads when, or more than 82 heads when you expected 50 because you tossed the coin 100 times. And then the median expected significance, that's a very sophisticated thing. Again, the significance relates to the p-value. You can imagine predicting different p-values or outcomes from an experiment. The median p-value for most situations would be half, because most of the time you'll observe the middle of the distribution and half of it is below and half is above if it's a symmetric distribution. But there are situations when you're trying to consider new physics signals or doing very sophisticated analysis where the median expected significance is not simply 1/2, it's something else. Okay. All right. Any other questions or comments about future things? You're very welcome. Yes, absolutely. Good question about the left tail from Shillong again. So if we land over here, again, an extreme value. So this is the next observed value. The extreme value here obviously means being far away from the bulk of the distribution. So now we would define the lower tail probability on the low side. So it's a little bit context dependent. Okay. All right, good. Any more questions? I love questions. Anything else? Okay, does not look like it. So let me bother you for just 2 more minutes to try to go through this chi-square distribution because it's the basis of least squares fitting, which I want to discuss with you. All right, so if we had new random variables independent of each other, we square those random variables and add them together and call that sum chi-squared, then chi-squared certainly is greater than or equal to 0, so not be a normal distribution. Normal distributions go to minus infinity, right? The distribution of this quantity depends on nu, the number of things that you added together, and it has this form. Okay, so this is the random stochastic variable that you're going to observe. This is actually related to a gamma distribution. This weird looking part out here just is normalizing stuff. And it's really, really important in hypothesis testing and in fitting. Okay, so here are some examples where you have only one variable or where you add 2 of them together, 5 of them together, 8 of them together. So you can see, of course, they never go negative because it's the sum of squares. but they can go out to infinity in principle. They have some special properties, and one of the important things is that the mean equals the number of things you added together. Okay, so if you add 5 things together, the mean is 5. Okay, if you add 8 things together, the mean is 8. It's skewed. That means it has a tail to the positive side, and the variance is just twice the number n, number nu. Okay, so it'll be identified with the number of degrees of freedom in the minimization problem. It's a sum of squares, a residual. So we'll talk about that, but this is the part that's interesting. As you add more and more things together here, as you add more and more, this goes from 5 to 8 to 50 to 500, then the variable chi-squared divided by nu becomes more and more sharp. Okay, so here's an example where in all cases, the mean of x is 1, but you can see that as I increase nu from 4 to 8 to 20 to 100, the distribution becomes more and more sharp, becomes more and more symmetrical. It becomes closer and closer to a Gaussian. Okay, and in fact, you can even use a Gaussian as an approximation. All right, so we will use these properties of the chi-square distribution when we talk about fitting, curve fitting, and so on. Okay, so a couple of good questions. Let me go back to those in my last minute or two, because I think there's a break. So when we're saying that we discover the Higgs boson at 5 sigma, which is a chance of 1 in 32.5 million, so it's exactly right. It pertains to usually this upper green tail that I drew here. All right, so it's because when we set up the problem, the lack of signal is usually at 0, and then the number x would be the number of events that you select, which will be positive. So it ends up being an upper tail probability or p-value rather than a lower one. And we will talk a lot more about that on Thursday morning. And then will we get a chance to talk about likelihood functions and the difference between, yes, in fact, Matteo, that is the subject for tomorrow's lecture, is maximum likelihood and least squares, minimizations, why these things are important, what the distinctions are. And it's in that context I'll also talk about combining measurements tomorrow. Okay. All right, so it's now, I believe, 3:30 in Denver. It's 4:30 in Chicago, where I am. We will talk about confidence levels, absolutely. I'll try to define them carefully. Andre, what should I do now?
That was a good time to stop, because we don't want to, run too quickly and then run out of steam, a week from now by exhaustion. On the other hand, yeah, but I think there'll be a lot more questions for the next few lectures. So we think, Michael, again, we don't clap because we know that doesn't work. And we hope to see everybody again tomorrow at 9 o'clock TASI time.
Okay, sounds great.
All right, thank you.
Yeah, thank you,
Thanks.
everybody. See you tomorrow.